Hello my friends, this is lecture 24, alternating current. Understand the relationship between alternating current, which shortly we call AC currents, and AC potential is in resistors, and understand transformers and how electric power gets to use in our homes. That's the idea here. Alternating current is generated when we actually change flux through a loop. You see in this figure here, loop is rotated in between two magnetic poles, north-south. We have magnetic field to the right. As the loop rotates, the angle changes and flux changes. Remember, flux is equal to A B cosine theta. In this case, theta keeps changing. In the figure, at the point you see, this is the normal to my loop or axis of the loop, and it keeps changing throughout. And what this will cause is a current in one direction as it rotates in this fashion, and then it will change to the other direction after this point here. The current will turn in the other direction, and the same will go for the EMF. As I keep rotating, the change will keep happening, and here is a graph of the induced EMF I would have. Increases positive, decreases to zero, then increases negative, and so on and so forth. This is the idea used in generators. It could also be the current loops are stationary, like in this figure, and magnet is rotating, so magnetic field keeps changing. And this is used in general electricity power generator resources. So as we talked about this here, induced EMF keeps changing. It's a sinusoidal change. It has a period and so on and so forth. It increases and decreases. And here is the equation to find it. It will have a peak value, epsilon 0, and it will change over the time. We won't be really dealing with this change in future of it. We will look at either its peak value or average value of it, and we will apply what we know from before, Ohm's law and so on, to solve for the circuits. So only new learning here will be, we have an alternating current changing, and we will be looking at the peak values or average values of that alternating current, or peak values, okay, and average values. And we will only look at simple resistor circuits. There are other types of circuits, but we won't be covering for those circuits. Everything we know from past works, Kirchhoff's junction rule works, Kirchhoff's loop rule works. Here is an equation. If we connect a resistor to an alternating current, here is how the potential difference across the resistor will change. Then again, we will look at its peak value. Here is a potential difference, peak values or average values of that potential. Then we will apply the rules we know. This is Ohm's law, you see here. Current is equal to V over R. VR is the potential difference across the resistance. This is showing the variable version of the current, but we will be using only its average or peak values. Unless it's specified otherwise, the values we're using will be what we call root mean square values. Those are average values of current, and the peak values will be called simply AR as IR or VR. So this is the peak value here. This is the average value, and it is of they are related. So average current is equal to peak current divided by square root of 2. That's an approximation, of course. And average potential is equal to peak potential divided by square root of 2. Then I can go ahead and calculate my power the same way as I was doing before. Here is average power loss in a resistor. And remember, we could calculate using I squared R, or V squared over R, or I times V. Only difference here, we are using root mean square values or average values. And this page is summarizing overall what we need to know. We are taking average values or peak values, and here's how they are related, but actually potential and current changes sinusoidally. And the only circuit we will cover in the AC circuits is the simple resistor circuit. Here how we symbolize the AC power, showing the sinusoidal change of the EMF. So EMF, or induced EMF power, or delta V, will be from alternative current source, so AC source. Power generators simply, or AC sources. Here is an example of how we will use this. The hot wire in a toaster dissipates 580 watts when plugged into a 120 volt outlet. Again, unless specified otherwise, these are RMS values. So I know now the power, it's equal to Vrms over R. I know Vrms, and I list them here. What is the wire's resistance? I'm looking for resistance from this equation. I can solve for resistance, right? V squared over power. What are the RMS and peak currents through the wire? For that, I would use Ohm's law. I RMS will be V RMS over R. That's it. And well, here is the solution. Or I can use the power equation, which is what is used over here. So we know the power is equal to I squared R. Power for the resistor can be written as IRMS. Squared divided by R, and solve for current. Here is what we will have. And of course, two approaches should give us the same answer. If I am looking for a peak current, after finding the RMS current, I will just multiply it by square root of 2. And here's how peak current and average current are shown in the book. So peak is as IR, current, peak current through the resistor, and this is the mean value or average value. As we generate alternating current, we want to carry them home, losing minimum amount of energy as possible. To do that, we want to increase the voltage. So to do that, we want to increase the voltage here, voltage increase, and we do that using what we call step-up transformer. It takes a low voltage and increases it. We send it through the wires, and as it comes out to our home, we don't want to carry 500 kilovolt of volt into our homes. Very dangerous, and none of the devices works with that. So we decrease it as we send it to our homes. And for that, we use what we call step-down transformer. So I want to talk about transformers a little bit. They are very useful in changing potential. We feed a potential on one side to it, and we can take out another potential to our desire and use it for a device that we are using. Very often used, and it works with alternating current, which is why we want to use alternating current in our homes. How it works is that we have a loop of wires on one side, an iron core, and loop of wire on the other side. We feed potential difference from a power source, and that power source, if it's an alternating power source, the potential difference will keep changing, and as the potential keeps changing, it generates a current. Of course, it generates a magnetic field. Let's say current is in this direction, magnetic field will be in that direction. There will be a flux through the second coil, right? That flux will keep changing, and it will keep inducing a current. That current and an EMF, induced EMF, and that current and EMF or potential will also vary. So we will have also alternating potential and current here, which we can feed to a system, home, or so on. That's how the transformers works. And how we control how much we want to increase or decrease, we can do both with the transformer by changing the number of turns. If I have higher number of turns on the left, I feed a potential difference and lower number of turns on the right. That will be a step down transformer. It will take a high voltage and decrease it. If I have the other way around, low voltage on the left, low number of turns on the left and high number of turns on the right, it will increase the incoming potential difference. Here is how we symbolize a transformer in a circuit. Here's how a real transformer looks. What we have here is flux changes right throughout the iron coil, and that flux change generates a current in the secondary loop, and we have an induced current and induced EMF. Flux change here on the left is the same as flux change there, right? So incoming potential difference V1 and outgoing potential difference V2 can be defined using Faraday's law. This is Faraday's law here. N1 delta phi over delta T. V1 is here. And V2 N2 delta phi over delta T. Since delta phi over delta T is the same in both sides, we can write V1 over N1 from here equal to V2 over N2. And from this equation we can rewrite more useful form, but you can also use this form of it. V1 times N2 is equal to V2 times N1. So if I know other three values, I can solve for a value. For example, I know N2, V2, N1, I can solve for V1, and so on. Here are how the transformers looks in real life. This would be our primary coil, and this would be our secondary coil, and here's how they look. And inside this box here we have a transformer. Any adapter you have, you connect to your phones or a lamp or any other device, are also transformers, changing the potential to adjust them to your device so your device will not be harmed. Again, step down transformer has more number of turn on the left and less number of turn on the right, assuming the incoming potential or power from the power sources are fed on the left. And step up has less winding on the left, what we call primary, and more. So step down N1 is larger than N2, and step up N1 is smaller than N2, and 1 and 2 being number of turns. Using the fact that the power in on one side of the transformer, primary coil to power out, well, here this would be the primary coil because here is the power source and here is how we use it out here. In power should be equal to out power. Using that and power equation, I1 V1 is equal to I2 V2 is another equation we can use here. Using the relation between N and V, we can get this equation over here too. So these are our relations you want to use. Again, generally we will be using RMS values, even if it may not be defined, they will be RMS values, and if we are asked for peak values, we will multiply that by square root of 2. Okay, these are transformers. Question here, if a primary coil of wire on a transformer is kept the same and the number of turns of wire on the secondary is increased, how will this affect the voltage observed at the secondary? and I'm gonna go to this equation for that. I'm interested in voltage and turns. This is the primary, and this is the secondary, and I'm interested in how this guy would change if, let me see again, primary coil of wire is kept the same, and number of turns in the secondary, this guy is increased. Alright, so what I'm gonna do here is I'm interested in voltage in the secondary, right? I'm gonna solve for that, and I can solve for that by dividing each side by n1. So I'm gonna have this n2 over n1 times V1. Now what I am doing, I am keeping this guy the same, and this guy is increasing. What happens to volt 2? Directly proportional. It will also increase. That is my answer there. Suppose that an ideal transformer has 400 turns in its primary coil. Stop and write down. N1 is equal 400. And 100 turns in the secondary, so N2 is equal 100. The primary coil is connected to a 120 volt RMS electric outlet, so V1 is 120 volt, and carries an RMS current of 10 milliampere. I1 is equal to 10 milliampere. What are the RMS values of voltage and current in the secondary? I'm dropping the RMS notation here. Keep in mind, if it's not specified, it's the RMS value or average value. So first let's find V2. I know N1, N2, and V1. I can find V2. Solve from here for V2. Divide each side by N1. V2 is equal to V1 times N2 over N1. That will give you V2. And then current 2, I2, will be I1 times N1 over N2. And put it in values, we can find what we are looking for. So V2 is equal to V1, 120 volt, and 2, 100. I put 1000 there, I just noticed. Sorry about that. It's 100 turns. Divided by 400. I can drop these zeros. 12 over 4 is 3, so 30 volt. And I2 here, I1 is, then I'm gonna leave it as milliampere because there is only one unit here, so it's safe to keep the same unit. N1 this time is 400, right? Right, that's right, that's 400, and N2 is 100. So in this case, I'm going to find I2 to be 40 milliampere. So this is my answer. This one is a similar question. Some values are given and some values are asked. I'm gonna give it up to you to decide and read it here. We show our transformer. V1 is 120. We don't know N1, N2 is 20 turns, and V2 is 4.8 volt. So we can use this equation, start from here, and solve for N1. So generally questions about transformers are of this sort. We can go ahead and solve for power and so on once we solve for, let's say, current and potential, right? Power is equal to current times the potential, I times V. Of course, these are again RMS values, average values. And this would also be RMS power, average power. Alright, that's it, my friend. I'm gonna put some solutions for questions I have in the following. I'm gonna leave the lecture at that. See you in the next video.